record. So what are we discussing? We are discussing the magnetic induction due to a bar magnet, and first we are calculating at an axial position of the magnet. So we are assumed a point P at a distance r from the center of the magnet. The magnet is of length 2d, pole strength is m, north pole, south pole over here. So the north pole will try to repel, or basically the north pole will try to create a magnetic field away, and south pole will try to keep a magnetic field towards. So basically both magnetic fields are in the opposite direction. So we subtracted them, and then we wrote the magnitude using Coulomb's law of magnetostatics. And then on further solving this particular thing, this will be equal to mu naught by 4 pi. From here you will get 4 times of r into d. You will pass 1 2 outside, and ultimately the overall result is twice of capital M. Well, what is capital M? It is twice of small m into d. I have already replaced it. Okay, and this will be r square minus d square by d square whole square. This is the magnetic field. Now what will happen for a short dipole? For a short magnetic dipole, the distance will be far greater than the length of the magnet. So r square minus d square will be approximated to r to the power 4. 1 r will get cancelled with 1 r, and the overall magnetic field will be equals to mu naught by 4 pi into twice of m by r cube. Or you can, if you don't want to write mu naught by 4 pi, you can write it as twice of k. If you remember, k is the constant by r cube. Do you remember? Can you see? The same formula was there for electric dipole as well, 2kp by r cube.
Yes, sir.
So the same formula is there for a small bar magnet as well. Is this clear? I'm just quickly going through it. If I want it on the equatorial axis, guys, do you want me to write the equatorial, the whole derivation again? It's fine. I think you people are able to do this particular thing because we already did it in electrostatics, right? Suppose this is your point P. This is the north pole, this is the south pole, this whole distance is 2d, and basically from the center of the dipole you want what? At a distance point P, what is the magnetic field? So now the magnetic field due to the north pole will be acting away from it, and magnetic field due to south pole will be acting towards it. Hence the overall field will be, and we know this particular thing, Bn and Bs, they both will be equal, and equal to mu naught by 4 pi into m into under root of r square minus r square plus d square whole square. Yes or no? Yes or no, guys? Will this distance be r square plus d square?
Yes.
And will this be d and d? So that's why. So, and if I say this angle is theta, this angle is also theta, so this is also theta. What do we call it? Alternate interior angles, and this will be corresponding. So what will the overall magnetic field? Can you see one component will get cancelled out, and only this will remain, right? So this will be twice of mu naught by 4 pi into m by r square plus d square into cos theta. What is cos theta? Can anyone see a triangle over here? T r theta r square plus d square. So cos theta will be d upon under root of r square plus d square. When you solve it, can you see twice m into d will be termed as capital M, and this will be r square plus d square to the power 3. This is the net magnetic field on an equatorial position. Passive income म्हणजे fixed income आहे, right? तेच ना. Passive income तर हेच होतं ना की तुमचं passive income for a short dipole. Active income ह्याच्यामध्ये जर काही per employee ला जेवढा भेटतं ते त्याचं active आहे. Self employee active पण असू शकतो, passive पण असू शकतो. Self employee passive कसं असू शकतं कारण की त्याला active income पण येतं आणि sorry. Time to equal money, right? Guys, please write this. I'll be just back. Let me just find my hanky. Hello. Honey, is it clear? The third derivation is basically at any general position, but this result is only valid for a short dipole. So suppose guys there is a small dipole over here. So if I make the dipole like this, that implies south will be over here, north will be over here, and let's say the magnetic moment is M. Let's say there is a point R at an angle, point P at an angle theta, right? Hello?
Yes, sir.
So there is a point P at an angle theta where you want to find out the magnetic field, and the magnetic field will be somewhat like this. Let me draw it for you. The magnetic field will be, let's say, like this. So I can have one component which is along the direction and one component which is perpendicular to this, right? So similarly, I can, this. Do you remember in electricity, electrostatics also, we just distributed this dipole into two dipoles. One dipole I made it like this, and another dipole I made it like this. This dipole will become m cos theta, and this dipole will become n sin theta. So can you see, for m sin theta dipole, this B2 will be at equatorial position, and m cos theta B1 will be in the axial position. So from here we wrote the formulas, if you remember, twice the same formula I'm applying. So B1, this radial one, will be equals to 2k, and P will be m cos theta divided by r cube. Similarly, B2 will be k m sin theta by r cube, and if I calculate the net total magnetic field, so B will be equals to under root of B1 square plus B2. So which, when you solve it, will be km by r cube into 1 plus 3 cos square. And that to root 819 months. Okay. So these are your formulas. You don't need to mark them up, but can you just see the relation with the analogy with electrostatics? Everything is similar.
Yeah. Yes.
See that. Don't need to mug it up. you can just mark the formula for electrostatic and automatically convert those formulas to these formulas. Please declare.
Copying the same thing is not a power. If anyone is opening the consensus chart, everyone is trying to open the same thing, then there is nothing to do.
Chalo, shall I give you questions?
Yes, sir.
Acha, do you remember P sin theta?
Yeah.
ये भी देख ही लेते हैं चलो. Force and torque on a magnetic field. The last topic also we can see, and then we can go with the questions and all. So suppose there is a magnetic field, a uniform magnetic field in space.
He is not using misuse the thing, then that is incompatible. Otherwise, that is not incompatible.
बाहर की लाइट चालू करो बाहर का. Suppose this is North Pole, this is South Pole. कभी कभी हमारे फ्रेंड लोग क्या है काउंसलर बन जाते हैं दूसरों के, है ना? So it happens. Hello guys. So suppose there is a dipole which is placed at an angle theta to the magnetic field. Can you see over here? This is South Pole, this is North Pole. So this will be the magnetic moment, capital M. Yes or no? Yes or no, guys? So here on this magnet, what will be the force acting? The force acting, overall force will be 0. Can you see MB acting towards left, MB acting towards right? The net force is 0. But is there a net torque? Yes or no? Will there be a net torque? And that torque will be equals to how much? And guys, in the case of dipole, what was the torque in vector form? Torque was equals to P cross E. So here it will be M cross B, and you can write it as MB sin theta. Please remember this formula is only valid till the field is uniform magnetic field. And acha, what will be the potential energy? Potential energy, if you remember, minus of P dot E. Yes or no?
Yeah.
Similarly, minus of M dot minus MB cos. So this is the potential energy. ठीक है. अच्छा, where is the reference considered when the magnet is? Where is the reference considered in this case? If you remember from electrostatics, when we say potential energy at point is this, so where is the reference? The reference is when the potential energy is 0. That applies when theta is 90 degree. So always remember कि when the bar magnet will be like this, कि south pole नीचे है और north pole ऊपर है, and magnetic field is like this. This is the reference point, okay? Or basically you can say when the bar magnet is perpendicular to the magnetic field, that point is the reference point. Not necessarily south pole niche hai fir or north pole is, doesn't matter, because cos 90 is also 0 and cos 270 is also 0, right? Then shall we start with the question part?
Yes, sir.
Once we're done with the question, we'll start with Earth's magnetic field, or basically terrestrial magnetic field today. Terrestrial magnetism. Suppose question is directly, I'll just write the statement. A bar magnet is 0.1 meter long and its pole strength is 12 ampere meter. Find the magnetic field. Easy question. At a point on its axis at a distance of 0.2 meter from its center. So here you will not be able to consider the dipole as small, right? Yes or no? Will you be able to consider the dipole as small? Is the length of the dipole very small as compared to the distance from the center? So you will not be using that formula B is equals to 2 km by r cube. No, you will be using the general formula, and if you don't remember it, derive it. Okay? No problem. So either remember it, so I don't mind. Mu naught by 4 pi twice of km under root of r square minus d square ka whole square. What is the formula? And please remember, the magnet is given 0.1 long. Please remember, this formula is when you have considered the length of the magnet as 2d. Okay, so basically your 2d is given how much? 0.1 meter. So hence d will be 0.05 meter. Yes or no, guys? थोड़ा सा be careful, है ना?
Yes.
Also, they have not given the dipole moment. The dipole moment is basically what? Twice of d into small m, which is basically twice of d is 0.05 and m is 12. So 2 into 12 is 24. 24 into 5 by 100 is how much? 1.2, I guess. Yes or no?
Yeah.
So m is basically this much ampere meter square. I can put the values now. Oh, my bad. And there is one more r. Twice of m into r, and this k is outside. R square minus d square to whole square. So mu naught minus to 10 to the power will be 10 to the power minus 7. 2 will be 2. M will be 1.2. R will be 0.05. And this will be R square. What is R?
So in the numerator also r will be 0.2 itself, right? It's the distance from the
minus T is 0.0. Now is it clear? Can anyone check once the formula is correct or wrong? Minod twice of m r square by g square. Correct. Oh, so when you'll solve the whole thing, the final answer which you'll get is 3.4 into 10 to the power minus 4 Tesla. That is the net magnetic field. And that's the answer. Okay. Calculation based, simple, easy. Next question. I'll not write the whole thing for you. Suppose there is a bar magnet, very small bar magnet, and this small bar magnet is suspended in a magnetic field with its north pole over here and south pole over here. Okay, this is the magnetic field. Can you see the initially the bar magnet is also horizontal, as well as the magnetic field is also horizontal, right? So now here the question is given: a magnetic dipole of magnetic moment M is suspended by a string in a uniform horizontal magnetic field as shown in figure. If in a horizontal plane this dipole is slightly tilted and released, then show it will execute show that it will execute simple harmonic motion. This magnet has a mass m and length so the length of the magnet is given to you, and this is given to you. Please remember, it is rotating in a horizontal plane. That implies what? When you look from above, will it look like this magnetic field is still going in this direction? And will it look like the magnet is like this? When you look it from, not in spite of the front view, go from the above and then observe it. Will you observe that north pole is still here and south pole is still here? And now this is the horizontal plane which they are talking about. So now when they moved it tilted by an angle theta, so let's say the final position of this particular thing is how much? This is the final position. So can you see at an angle theta? They have just tilted it by a very small angle. Now what will happen when this small angle will be there? This there will be MB acting over here, there will be MB acting over here, due to which what will happen? This magnet will try to come back to its original position, right?
Yes.
So we can write if dipole is tilted by an angle theta by a very small angle theta, then the restoring torque, what is this restoring torque? That torque which is acting on this dipole is trying to make it back to that same position, right? The restoring torque on magnetic dipole will be, the torque will be equals to mb sine theta. And we all know about trigonometric approximation. If theta is very small, then sine theta can be approximately treated as theta, but theta shall be in radians. Okay, we know the trigonometric approximation, so I can write this as torque is approximately equals to m into b into theta. Yes or no?
Yes.
Now this torque will provide certain angular acceleration. So angular acceleration will be equals to what? I into alpha? Yes or no? So from here, alpha will be equals to torque divided by moment of inertia. Torque is mb theta, and what is the moment of inertia? Can you see this is in the shape of a rod, and this rod is trying to rotate about its center. So what is the moment of inertia of a rod about its center? Chapter rotational motion.
Yeah.
ml square by 12. Very good. So ml square by 12. Please remember, this mass is the small m. They have given mass is small m, right? So small m L square by 12, and from here I can solve it. Can I write it as 12 mb upon ml square? Can I write it like this? Into theta, and will this be the restoring torque? If this will be the restoring torque, then क्या होगा? Oh, sorry, my bad. This will be the angular acceleration, and can you see acceleration, displacement, and we know the equation of restoring. Do you remember equation of FHM? So this is basically equals to what? Omega square. So from here, when I compare, omega will be equals to under root of 12 mb upon ml square, and from here I can find out the time period as 2 pi under root of by omega, 2 pi divided by omega, right? That will be reversed. Always remember, from this omega, whenever you need to find out time period, so basically reverse whatever is written inside this root and add a 2 pi in front of it. I think we already discussed all these tricks in simple harmonic motion, if anyone remember. So basically, can you see this is executing SHM, and what is the time period of that SHM? Ye raha. Okay, please note the whole thing. I think you need to note it from here only. You might have noted till there.
जोर से बोल रहा था क्या मैं?
बहुत
ओके एक हमसे पोलर लगा से बिटला रे हां
भाई क्लास मेरी चल रही है.
Sami 6 mark कर रहे हैं.
Done भाई.
कुक नहीं आता ना.
Guys, are you done?
अरे हम तो कुक ना.
Yes, sir.
है ना सारे तो
Chali. Let's write about Earth's magnetic field. So heading डालें. I think OVA is facing difficulties with some net connection. Hello, OVA. Hello. Anyways, give the next heading. Earth's magnetic, also called as geomagnetic. Okay. The first thing which we'll write in this particular thing is basically what? The study of characteristics of Earth's magnetic field is called as terrestrial E as well. Terrestrial magnetism. Okay. Now, what is this? Why do we have the Earth's magnetic field? So people have given, initially when we people discovered that Earth also creates any magnetic field of its own. Then there were several theories on which people said. The first theory was basically, suppose if this was Earth, so they said that there is a, suppose this is the axis of rotation of the Earth. So they assumed that there is a huge magnet, imaginary bar magnet inside Earth. So the first theory was basically assumption of a huge imaginary bar magnet inside Earth. And obviously, this theory failed, right? Because I literally don't believe this theory whether there will be a huge magnet inside Earth. ऐसा नहीं होता. The one which makes much more sense is basically the second theory. And sir, you'll ask, I'll answer all your questions. Why, sir, have you drawn the uh, magnet a bit tilted? We'll talk about it later. Axis, suppose if this is the axis of rotation, then the magnetic field goes something like this, about like this. It goes into the North Pole and comes out over here. Yes, sir. This is how the magnetic field is there inside Earth. And this is how the magnetic field of Earth is there. Are you getting my point? It was found to be like this. It was found to be like this. So that's why, we assume there should be a huge bar magnet inside. So from the magnetic field outside the Earth, they said that there is a huge bar magnet inside. But this theory doesn't make any sense. The more appropriate theory is basically the second theory. The second theory says that inside the Earth, when Earth was formed, so what happened? Suppose I'll try to draw it as I'm thinking. Suppose this is your Earth, and let's say the Earth is rotating about this axis. Basically, what is this? This is the axis of rotation of Earth. It is found that the Earth's, this particular thing, there is molten metal inside the core of Earth. Yes or no? Everyone, I think, knows about this fact, right? There is molten metal inside the core of Earth, molten iron and other heavy metal alloys. So basically, this is the core of Earth. contains molten metals, especially iron, cobalt, and other heavy metals, etc. Okay, so all of them are in the molten metal form. Now, when this Earth was forming, people still don't know the reason what happened. But it is found that the rotation of the molten metal inside the Earth, it's not exactly same as the axis of rotation of Earth. The molten metal inside the Earth is rotating at a little bit angle. So if I say that this is a molten metal particle, so this molten metal particle is not rotating like this in the direction of Earth. It is not rotating like this. It is rotating at certain small angle like this. Okay. And now due to this rotation of this particular thing, can you see whenever you have molten metals, they will be in the form of ionized form, right? They will be in the form of ionized ions. Yes or no? If they will be ionized, that implies they will have certain charge on them. Are yes or no? So if I have some charge which is rotating in a circular motion, so will it be? Can I say will it produce an equivalent current? So you can write this theory as the molten metals or alloys inside the Earth's core rotate at a certain angle to the axis of rotation of Earth. This implies, by the way, this implies that the axis of rotation of molten metals and axis of rotation of Earth is different, है ना? Axis of rotation of Earth and axis of rotation of molten metals is at a slight angle with each other. So that angle is approximately 11 degrees. Please remember this angle keeps on varying with time. This angle is not constant, enough. Sometimes it varies from 10 degree to 13 degree. So this angle keeps on varying with time to time, not necessary. So angle approximately equal to 11 degree and like this. So it's like this. I'll draw it again. Let me draw the Earth with blue. Let me draw the axis of rotation of Earth. Let me draw the core with red. ये actual diagram बना रहा हूँ. But the molten metals inside the core, they are rotating at certain angle. And due to which what happens? The axis of rotation of this particular thing, I'm drawing it with green. Can you see over here? This angle is approximately equal to 11 degrees. I'll write the whole thing. People still don't know the reason why does this happen. Even if you find some reason, then tell me what are the theories behind it and all. Because I told you, I never prepared for this chapter. If I would have prepared, then I would have gone to the roots of every problem. Ki why is this? You don't know me. So axis of this is the axis of rotation of Earth, and this is the axis of rotation of molten metal. Okay, is this clear, guys? Guys, is this clear?
Is it 11 degree? Or,
Your voice is breaking, beta.
is it 11 degree? Here it
11,
is
11,
110.
approximately 11 degree. Oh, sorry. Oh, my bad. Okay. Approximately 11 degree. So is this fact clear, guys? Hello? Is this fact clear, guys?
Yes, sir.
Yes, sir.
So first fact was this, कि basically the Earth's axis of rotation is different and the molten metal inside the Earth, they are rotating at certain angle. Please remember, 11 degree is not a big deal. And 11 degree is very much, we generally ignore this angle. We consider it as small only, no? I told you, no, angle till 10, 20, 10, 15 degree, we consider it very, very small. Right?
Yeah.
So it's a very small angle, doesn't matter that much. But due to this thing, a lot of things has changed. Because the size of Earth is big, no? So that's why. So anyways, we can assume that the molten alloys or metals being ionized एक second guys, give me 2 minutes. Hello, मैं क्लास में हूँ, I'll call you later. So we can assume that the molten alloys, metal being alloys or metals being ionized, revolve in the circles in the core. So whenever a charge particle, please remember, whenever a charge particle, it rotates in circles. Suppose if the charge is q and the radius of the circle is r, and let's say this charge is revolving around with an angular speed omega, right? Then we can say an equivalent current is flowing in this circular circuit. So always remember, whenever a charged particle is revolving in circle, we can assume that this is not a charged particle. This is basically a what? This is This is basically a current carrying coil of the same radius. Are you getting my point? And what is the current flowing in it? Since it's a positive charge, the direction of rotation of this and this will be the same. So we can assume that it is an equivalent current is flowing in this circuit. The value of this I equivalent is given by, if you people don't remember, charge by time period. Time period is given by 2 pi by omega, and can you see q omega? So you can calculate this. This is what I'm saying. Okay. So
Yeah,
now,
okay,
if
sir.
this current carrying conductor is there, then there will be certain magnetic field also produced by it. Yes or no? So if you assume that the Earth is going like this, that the Earth is rotating in that direction, then can you tell me what will be the direction of magnetic field? Is it clockwise or is it anti-clockwise? Whatever it is, can you see over here?
So could you repeat that?
If there is a current carrying coil, then will it produce certain magnetic field?
Yes.
This current also, this is also hypothetical, but we can assume that this theory is making much more sense as compared to the previous one. This current leads to the Earth's magnetic field. So basically, this theory made much more sense. So that's why we are discussing this particular thing. Because of this,
How are we related the coil to the earth? I don't get it.
we are not relating it with the coil. We are just saying that the charge is rotating,
Okay.
and it's in the molten form, no? So the ionized form charged are rotating around the inside the core. So those were rotating.
Fine.
We assume those charges to be in the form of a coil. Don't say like this, sir, is there a wire inside her? No,
So I get it.
no
Yeah.
wire. And it's just some charges which are revolving around the axis. So we can assume there is an equivalent current flowing, and that is what is responsible for the production of magnetic field. And due to
Okay,
this
fine.
equivalent current, we can say a magnetic field is produced inside Earth, and I'll draw that magnetic field. It looks somewhat like this. Are you getting my point?
Yes, sir.
This is basically the cause of Earth's magnetic field. So this theory made much more sense to me. So you will write this theory. This is the cause of Earth's magnetic field. And what is the main reason? It is due to the motion of molten heavy metal alloys in the inner core of Earth. Okay, so due to the motion of molten heavy metals. Please remember, whenever I say heavy metal, first thing that should come to your mind is iron alloys, na? Iron. So alloys in the inner core of Earth. So that is the theory which is cause of Earth's magnetic field. Okay. No, I don't go with this, but generally still I'll try to explain it with the help of this as well. Please remember this magnetic field which is formed. The magnetic field which is formed, is it just like various coils in which the current is flowing, right? Can I assume number of coils inside over here? There is this coil, there is this coil. Yes or no? Can I assume there are number of coils inside there, inside the Earth's core like this, which get formed? Hypothetical coils, not really. So, anyways, Acha, by the way, the region in around the Earth's atmosphere, or basically the region in the Earth's atmosphere where the magnetic field exists, is basically called as what? The region in the Earth's atmosphere till where the magnetic field exists, as though it exists till infinity, right? We all know this particular thing, but infinity doesn't exist. At one particular time, it will be of so much negligible value that you won't feel it anymore, right? Is basically called as magnetosphere. Okay. Is this clear?
Yes, sir.
One. There are some points to note. If you want to relate it with the help of the first theory, there are some points which we can write. The first point is the magnetic field lines due to Earth's magnetic field resembles that of a bar magnet. basically this thing was responsible for your theory 1. The magnetic field which people observed of Earth, it was similar to, that of a bar magnet. So people said कि अरे शायद से there is a huge magnet inside Earth. Okay, the magnetic field looked like this. Somewhat, not everything. It somewhat looked like that of a bar magnet. So people assumed कि अच्छा शायद से there is a bar magnet over there. Okay, and this bar magnet has a south over here and north over here. Why south north? We'll discuss in the next one. Okay, is this clear, guys? First point clear? Let me do one thing, since it will be lots of diagrams. So let me just shift the diagram. Okay, first point clear? First diagram also clear, right? Yes or no?
Yes, sir.
Let us define something called as poles of Earth. Everyone knows poles, right?
Yeah.
Second point. The second point is basically this: suppose if this circle, this sphere is there and it is representing what? What is this, guys? If this is my Earth and this is the axis of rotation of Earth, so tell me, what are these points? We call them the geographical north and this point I call it as geographical south. Yes or no? I'll denote this by, let's say, NG, and this I'll denote by SG. Okay, yes or no, guys? But we know this particular thing, that the magnetic axis, this is basically the geometrical axis of rotation, right? But the magnetic axis of rotation is somewhere else. Yes or no, guys? Can you see this? This is the magnetic axis of rotation. The blue one is basically the geographical axis of rotation, or you can say the actual axis of rotation, the true axis of rotation. But the molten mirror, this is basically what? The magnetic axis of rotation. Yes or no? What is the angle between them?
Approximately 11.
Angle between magnetic axis and geometrical axis is approximately 11 degrees. Okay. But due to this particular thing, can you see over here, when you observe the magnetic field of Earth, when we observe the magnetic field of Earth, Has the diagram become too much detailed? It's fine. This particular point is basically called as NM, and this particular point will be called as SM. Why NM and SM? What is NG and SG? Geometrical north and south, and this is your magnetic north and south. Yes or no? Now, always remember third point. A magnetic needle in any point in space. Please remember, I'm not talking about the general 3D space. I'm talking about the space. You know, the one which is outside Earth space, okay? I'm talking about this particular point in space, right? So whenever you have any point P in space, then always remember this point P, if you have a magnetic needle, it will never point towards this NG. It will point towards this NM. Okay, so a magnetic needle in any at any point in space around Earth always points towards the magnetic north. Okay, you just need to keep it aligned in that direction, so always it will point towards the magnetic north. And that is the reason why I told you in the beginning of the chapter, I told you it points approximately towards the geographical north. Yes or no? Because actually it is not pointing towards the geographical north, it is actually pointing towards the magnetic north. Are you getting my point, guys? Is this clear? Hello?
Yes, sir.
Is
Yes,
it clear
sir.
now? Okay, now the magnetic needle is not actually pointing at the geographical south. It is pointing towards the magnetic south. Not actually pointing towards the geographical north. It is pointing actually towards the magnetic north. But since they are at a certain angle, due to which exactly they are not at the same position, right? So that is why I said you will reach approximately towards the North Pole. At that instant, the yesterday's lecture, I used the term approximately somewhere now. So this is the reason why. Okay, is it clear? Is it clear, guys?
Yes, sir.
Yes, sir.
If I divide it like this, then you know, next point I will divide. So I guess you are clear in the geographical north and geographical south, magnetic north and magnetic south. Clear? I guess you are clear about this particular. Now, sir, why did we name the magnetic north and magnetic south over there? There is a reason behind it. And what is that reason? See, when we observed the Earth's magnetic field, then the Earth's magnetic field was observed to be in this particular way. Suppose this is the magnetic axis. Suppose this is the magnetic axis of Earth. This is the North Pole. And why did we name this as the magnetic north and this as the magnetic south? Why did we name this as NM and this as SM? उसके पीछे एक reason है. Since we were initially unaware of the magnetic, we were initially unaware of what? We were initially unaware of what? Hello? We were initially unaware of what? The magnetic field of Earth. So conventionally we have taken this particular thing, that whatever lies above in the above part is basically in the northern hemisphere. So hence we assumed this as what? North Pole, right? जो भी कुछ ऊपर था, we assumed it as north. कन्वेंशन के अनुसार we have already decided this particular factor. अपने पूर्वज लोग डिसाइड करके चले गए थे. Yes or no? Later on, when the Earth's magnetic field was observed, then this Earth's magnetic field was somewhat like this. Let me draw it for you. Just give me 2 minutes. So the Earth's magnetic field looks somewhat like this. Suppose this is the surface of Earth, na? And I'm drawing in this plane. So there will be certain lines which will be like this. Is everybody able to feel the lines where exactly these lines are? These are coming out of the surface of Earth at different points on Earth. Yes or no? I'm just drawing one in one particular plane. This is happening. It was something like this. When people try to go at different points, they assume that the lines are coming into the plane over here. With the help of a magnetic needle, you can predict the direction of magnetic field, right? And the lines were going out of here. So whatever it was there, different points in the northern hemisphere, it was like magnetic lines were getting into the Earth. In the northern hemisphere, the magnetic field lines were assumed to be going into the plane, whereas in the southern hemisphere, the magnetic field lines were assumed or were observed coming out of the surface of Earth. We can write this particular fact as well. In the northern hemisphere, the magnetic field lines were observed to be going into the Earth, whereas in the southern hemisphere, so always if I have any point on the northern hemisphere, suppose this is the ground level. Suppose you are standing at any point on the ground in on Earth in the northern hemisphere. Suppose this is the point and you are standing like this. You are not that big, obviously, है ना? But you are standing like this. The ground will look like this to you. Yes or no? Along the tangent. So at any point in the northern hemisphere, if you are standing like this, then you'll observe that the Earth's magnetic field is going into the ground like this at different points. But it is at certain angle. By the way, this angle will be later on named as angle of inclination or angle of depth. Whereas in the southern pole, if you are standing somewhere over, let's say here, so you will be standing like this. ये clear है guys आपको? You are like this only, no? Don't think like you are standing like this. On the southern hemisphere, you will not fall from here. Everyone understands this particular thing, यार सबको gravity समझ में आती है, I guess. Everyone understands how gravity plays role, right?
Yes, sir.
So suppose if you are standing like this in the southern pole, then if I draw this like this, so again suppose this is your ground, you're standing like this, and then you'll observe that the magnetic field is coming out of the plane, out of the ground. So this is what was the difference between northern and southern hemisphere. And now, since people observed this and they wanted to give the theory where the magnet used to be there, right? Yes or no? So basically, what did they do? They assumed that when there was a magnet, this magnet has a south pole where the north pole is there, where the magnetic north is there, and they assumed the north pole where the magnetic south was there. So basically, if they assumed like this, then can you see it clearly now? The magnetic field coming out of the north pole of the magnet, right, and going into the south pole of the magnet. Hello.
Yes,
So
sir.
now you understood what was the reason of the first point where I drew south here and north here, even if the magnetic field was going like this, right? So due to some phenomena observed, we developed these theories. Now I understood the reason before for the why it is south and why it is north. Yes or no?
Yes, sir.
चलिए. So ये थोड़ा सा याद रखना. Yeah, I told you about this particular thing. If it goes into the ground, let me draw it over here. Control X. Okay. Acha, what does BE represent? What is this B upon subscript E? This is the Earth's magnetic field. Okay.
Okay, sir.
So after this, there is one more point which is based off equator. Everyone knows equator, right? So equator is also two different types of equator you have. One is the magnetic equator and one is the geometric equator. So again, this is my Earth, right? This is the axis of rotation of Earth. So this, do you remember this? Yes or no? What is this equator? This is your geometrical. Shall I define equator? Ki everyone knows equator, right? Yes or no? And similarly, if this is the magnetic axis, then this will be the magnetic equator. So till what points will you observe that the magnetic field is going into the plane? Whatever is lying in the northern region of magnetic, can you see whatever lying above this magnetic equator? That is my magnetic northern hemisphere, right? Yes or no, guys? Geometric northern hemisphere and magnetic northern hemisphere. So whatever points are lying above the magnetic northern hemisphere, I'll observe that the magnetic field, the Earth's magnetic field will be going into the ground at this particular point, and at this particular point it will be coming out of the ground. We'll discuss about some more points, how exactly a needle will be, if I place a needle at the poles and if I place a needle at the equator, then how exactly will they point? We'll see them in the next class. Just draw about geometrical equator and magnetic equator. And we'll see how where a needle points at poles and at equator. Achha, which equator and which poles am I talking about? Guys, which equator and which pole am I talking about? I'm talking about magnetic poles and magnetic equator. Okay, is it clear? Is it clear? Till here, is it clear, guys? Earth's magnetic field.
Yes, sir.
Yes, sir.
Okay, chalo, ठीक है. Any doubt till here? No.
No, sir.
How is it? How is the chapter going for my first time teaching this?
Really good.
Really good, no? समझ में आ रहा है, चलेगा, कोई दिक्कत। चलिए guys, thank you very much. We'll see you again in the next class, and we'll discuss some more things. Na? There is something called as tangent galvanometer also, which I need to teach you.
Okay.
Chalo. Okay. Tata.
Thank you,
Bye.
sir.
Thank you, sir.
Bye.
Thank you, sir.
Thank you, sir.
Sir.